This video will cover the formation of enolates. Enolate ions are formed following treatment of an aldehyde or ketone with a base. Several different bases can be used to perform this deprotonation reaction. Oftentimes, hydroxide or an alkoxide ion is used. Remember that acid-base reactions are equilibria, and that the equilibrium will favor the formation of the weaker acid-base pair. The ketone or the aldehyde is the acid, and hydroxide or alkoxide is the base, making the enolate the conjugate base and water the conjugate acid. Remember that we can compare the strength of an acid using its pKa value. The pKa of a ketone or an aldehyde is around 20. The pKa of water is 14. A smaller pKa value indicates a stronger acid. Therefore, water is a stronger acid than a ketone or an aldehyde. This means that the ketone or aldehyde and the hydroxide ion are the weaker acid-base pair. Therefore, this equilibrium lies to the left. Reactants are favored. Treating a ketone or an aldehyde with hydroxide ion or an alkoxide ion produces the enolate, but only in very small amounts, because this equilibrium favors the reactants. For some alpha substitution reactions, however, even a small amount of enolate can still be enough. This is because the enolate is being used up in the alpha substitution reaction. Let's look at an example. If we treat this ketone with hydroxide ion, it will produce a small amount of the enolate. This equilibrium lies to the left and favors the ketone and the hydroxide ion. The small amount of enolate that is formed, however, can react with the electrophile. If the second step is favorable, the equilibrium lies to the right. If the second step favors products, this helps to remove the enolate ion from solution. Le Chatelier's principle states that the equilibrium will reestablish itself to compensate for the lost enolate product, making the first equilibrium lie further to the right. In this way, even a small amount of formed enolate can be enough to result in the alpha substituted product. In some cases, however, a small amount of enolate isn't enough. In these cases, we use a very strong base to convert the carbonyl entirely to enolate. Typically, the strong base that we use is called lithium diisopropylamide, abbreviated LDA. The structure of LDA looks like this. LDA makes a good, strong base to use to convert the carbonyl to enolate because it is non-nucleophilic. It is strong but bulky, so it cannot compete with the enolate for the electrophile. Using a strong base such as LDA helps push the equilibrium for the enolate formation to the right and produces the lithium salt of the enolate ion. Once formed, this lithium enolate can be reacted with an electrophile in an alpha substitution reaction.